Section 9.2, Part 1, Confidence Intervals about a Population Mean. Lesson objectives: state the properties of the student t-distribution, determine t-values using a table. Lesson objective: suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals x bar minus mu divided by s divided by square root of n follows a student t distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. Now what does this really mean? This means we're going to introduce a new distribution. We've talked about the z distribution, and we're going to look at what's called the t distribution. To give you a little bit of history about the t distribution, the inventor was a gentleman named Mr. Gossett, who worked for Guinness Brewing Beer Company. His job was to make sure the beer's quality was up to standards of Guinness. He was doing hypothesis testing, and he was rejecting about 15% of the beer when he should have only been rejecting about 5%. So there was something that wasn't right, and he hated wasting all the beer. So he figured out when he used the standard error, s divided by square root of n, the shape of the model changed. He figured out what this new model was, and he called it the t distribution. Let's look at some properties of the t distribution. The t distribution is different for different degrees of freedom. Now, what is a degree of freedom? We'll talk about this in just a little bit. There is a formula for the degrees of freedom. Number 2, the t distribution is centered at 0 and is symmetric about 0, just like with the z. Number 3, the area under the curve is 1. The area to the right of 0 equals the area to the left of 0, which is 1/2, 0.5. Number 4, as t increases without bound, the graph approaches, but it never does equal 0. We call this an asymptote. As t decreases without bound, the graph approaches, but it never does equal 0. Number 5, the area and the tails of the t distribution is a little greater than the area and the tails of the standard normal distribution. This is because we are using s as an estimate of sigma, hereby introducing further variability into what's called t statistic. Now that t statistic is what we saw a few slides back. T equals x bar minus mu divided by the quantity s divided by square root of n. Number 6, as the sample size n increases, the density curve of t gets closer to the standard normal curve. This result occurs because as the sample size n increases, the values of s, the sample standard deviation, get closer to the values of sigma, the population standard deviation, by the law of large numbers. So here's the visual. If we look here, the normal is the diagram with the blue outline. It has the highest peak. The next one is the pink line. That is a t distribution where sample size is 15. And then the orange outline, the smallest hump here, but it has more area and the tails. This is t with a sample size of 5. So as you take a t distribution and you increase the sample size, it will approach a standard normal distribution. Lesson objectives. Now with the t distribution, we're going to use a new table, and in that table you read it differently than we did for the standard normal table. Instead of giving you area to the left, now this table gives you area to the right, and this area is equal to what we call alpha. So the notation would be t sub alpha. Let's do an example. So here's table 6. Our degrees of freedom are the rows, and the columns are actually area. Now that is different than table 5. these numbers in the body of the table, if you'll see here, they're almost all larger than 1, and the reason why is these are actually t values, and these are probabilities. Okay, so let's do an example. Find the t value such that the area under the t distribution to the right of a t value is 0.2, assuming 10 degrees of freedom. That is, find t sub 0.20 with 10 degrees of freedom. So if we go to the table, 10 degrees of freedom will tell us what row, and since we want area to the right for 0.20, that tells us the column, and then we see this is our value of t. So the value of t, where the area to the right is 20%, is, according to our table, 0.879. Now, because we are doing confidence intervals for 90%, 95%, and 99%, we only need to focus on 3 columns. The first column would be the 0.05. That corresponds to a 90%. And the reason why is this value is our alpha divided by 2. The table is saying the area to the right is 0.5, but we have a left tail that has the same area, so 5% plus 5% gives us our alpha level 10%. So that corresponds to a 90%. 95%, we would use this column, and a 99, we're going to use this column. So these are the 3 columns that we will use for confidence intervals. Now, if we looked at the bottom of the table, we can see that we have degrees of freedom from 1 to 40. Then after 40, it goes 50, 60, 70, 80, 90, then 100, and then 1,000. And then we see at the bottom, actually, the t after 1,000 becomes identical to the z. So if we have a sample size of 43, our degrees of freedom is n minus 1. So if you have a sample size of 43, your degrees of freedom will be 42. Now there's not a 42 in the table 5, so you just round that off. Is 42 closer to 40, or is it closer to 50? So you would use degrees of freedom of 40. If the sample size is 56, then the degrees of freedom is n minus 1, 55, and there's not a 55, so is 55 closer to 50 or 60? Well, we would round that to 60. So we would use the degrees of freedom for 60. If the sample size is 88, our degrees of freedom is 87. 87 is closer to 90, so you would use a 90. If our sample size is 123, degrees of freedom would be 122. And of course, between 100 and 1,000, 122 is closer to 100, so you would use 100. And the last one, if we have a sample size of 554, the degrees of freedom would be 553, and 553 is closer to 1,000, so we would use 1,000. Okay, let's do some examples here, reading in the table. So if the sample size is 14, our degrees of freedom is 13, and these are our corresponding t values for a degree of freedom of 13. So again, this is going to correspond to a 90%, this is for a 95% confidence interval, and this one will be a 99. If we go n is 31, degrees of freedom 30, and we have our corresponding t values for the different confidence levels. 53 has a degree of freedom of 52, and we have our corresponding values. If we go to 300, degrees of freedom is 299, and we have our corresponding t values. If you see, as the larger n gets, the more the t approaches the z. So if we were to look at this for a z, this would be 1.645 For a 95, this would be 1.96, and for a 99, this would be 2.575. Thanks for watching.